Hey everybody, thanks for watching. Welcome back. Don't forget to subscribe to the channel. We've got a whole bunch of trigonometry, pre-calc, calculus 1, 2, 3, linear algebra, and proofs on the way. Feel free to share that with your students, your math colleagues, and your friends that enjoy mathematics. And with that said, let's get into our linear algebra for the day. So one, we want to show that these two column vectors are eigenvectors of the following matrix. And two, if P is equal to this matrix, we want to compute this product. So P inverse times A times P, where A is exactly this matrix. And in order to get there, we're going to need some classic math tools. And so one, we're going to need the mighty Euler's formula. Now two, we're going to need the property that cosine is an even function. That's very helpful. Three, we're going to need the property that sine is an odd function. That's also helpful. And then four, we just need some properties of imaginary numbers. Okay, so with that said, let's dive right in. So first, let's work with this column vector. Let's go ahead and show that this column vector is an eigenvector of the matrix A. So we want to compute a product. Okay, so we're looking at the following. So we're taking the matrix A, and we're going to multiply by the column vector 1i. And so that should give us the following. So the matrix A, we've got, looks like cosine of theta, and then below minus sine of theta. And then here we've got sine of theta, and then cosine of theta, and multiplying by the column vector 1i. Okay, so here we just want to be careful, and then we'll end up being just a little clever. Okay, so we've got, looks like cosine plus I sine of theta. That's very nice. So cosine of theta plus I sine of theta. And then down here, it looks like minus sine of theta plus I cosine of theta. Okay, so I'm pretty happy about this. We know by Euler's formula, this is exactly e to the I theta. And this, we've got to do a little bit of algebra. So here's where we get to be just a bit clever. Now, we know that I squared is equal to minus 1, right? So I squared is equal to minus 1. That means we can rewrite this. Let's actually factor out an I. And since I times I is minus 1, this is just fine. And so if I factor out an I, that's taken care of right there. So that seems really nice. So doing things like this will be key to today's linear algebra work. Okay, so let's take a look here. So by Euler's formula, we have the following. So cosine of theta plus I sine of theta is exactly e to the I theta. And then here, of course, by the commutative law of addition, we could think about this as cosine of theta plus I sine of theta, which is also e to the I theta, but we've got this little factor of I here. Well, we can write this as e to the I theta, and notice our original vector pops up. So this is exactly the definition of an eigenvector. And so 1i is an eigenvector of matrix A. Okay, so in sort of the same spirit, we're going to go ahead and check the other column vector now. And so let's see what we have here. So now we want to check, so A times the column vector I1. And again, we said that the matrix A was cosine theta minus sine theta. And then we've got sine of theta, cosine theta. And that's times the column vector I1. And really, this is just more of the same. We're going to multiply out. We're going to be a bit clever with the goal of finding Euler's formula and then factoring so that we get the definition of an eigenvector. Okay, so here we go. So row by column, this gives me I cosine of theta plus the sine of theta. And then here, this gives me, well, negative I sine of theta plus the cosine of theta. Okay, so let's take a look here. So here I think I'm gonna factor out an I. So let's go ahead and factor out an I and see what happens here. So if I factor an I out rather, looks like I get cosine of theta. Now I know that I times I, so I times I is minus 1, but I want a plus. So let's make that minus so that the product would be minus 1 times minus 1, so for plus 1. So that's where we're being just a little bit clever. Okay, thinking about combinations of these I products. And then down here, let's see what's going on down here. I think we can just rewrite this, right? So we can write this as cosine of theta minus I sine of theta. Okay, so being clever, so thinking about properties of even and odd functions, we can think about this in the following way. So I know since sine is an odd function, I can, in a sense, sort of tuck this minus 1 back in with the angle, really just by definition of an odd function. But cosine is an even function. So since cosine is an even function, that means that cosine of minus theta is the same as the cosine of theta. So this is the same thing as this. And again, this is where we're being just a little bit thoughtful and a little bit clever. And so again, since sine is an odd function, that gives me exactly this. Okay, well, if that made sense, I mean, this is really just more of the same. So down here, this should be exactly cosine of minus theta plus I sine of minus theta. So again, just using the fact that cosine is an even function and sine is an odd function. Well, by Euler's formula, that gives us the following. So we've got I times, looks like e to the minus I theta. And then down here, this is e to the minus I theta. But I can write this exactly in the following way. So this is e to the minus I theta times the column vector I1. And so again, we see the definition of eigenvector. So this must be an eigenvector for A. Okay, so that finishes the first part. So again, that means we've got A times vector equals lambda vector. Okay, so that seems pretty good. Let's work on part 2. So let's take a look at the problem just once more. Okay, so if P is this matrix, we want to compute this. So I think in a sense, since these are eigenvectors, this will give us, with proper algebra, a way to diagonalize A if we're careful. But we're not going to take it all the way to, we'll have a diagonal matrix, we'll see, but we'll maybe just leave it at this product. But keep that in the back of your mind. So yeah, with that said, let's go ahead and work with part 2. Okay, so first it would be nice to have, probably be nice to have P inverse, right? So remember how to find the inverse of a 2 by 2 matrix. So this is 1 over the determinant of P. So the determinant of P, so this would be product minus product. So watch what happens though. If I've got product minus product, so that's going to be, 1 squared minus I squared. But I squared is minus 1. So this will just really be 1 over 1 plus 1, or 1/2. And then be careful what happens to the entries in the inverse, right? So if I'm dealing with the inverse, then, well, these will switch. So this will be 1 and 1, and these will negate. So this will be minus I and minus I. And I'm going to keep the 1/2 here. I think it's going to make our computation much nicer. I could distribute this, but I don't need to. As long as I'm careful, I've got properties of matrices on my side, and that makes me happy. Okay, so here we go. We've got P inverse. So now our job is to do this big multiplication here, right? So P inverse times A. So P inverse times A times matrix P. Okay, so what does that mean? It means I've got P inverse times the matrix A, and the matrix A was, remember, that was cosine of theta, and then minus sine of theta, and then sine of theta, cosine of theta. And then lastly, we want to multiply that by the matrix P, but the matrix P was 1, positive I, whatever that even means. So 1I, 1. Okay. And then, of course, we can use the fact matrix multiplication, as long as we're defined nicely, and we are, is associative. So we can go ahead and multiply this in maybe a convenient way if we want to. So if we want to, we can go ahead and do this first. That's just our choice, but we're free to do that. So what do we have here? So here we've got to be kind of careful. Give myself some room here. Okay, so row by column here. So row by column here, right? So row by column, so this will be product plus product. That's going to be cosine of theta plus I sine of theta. I'm not going to get too excited about that until we're finished multiplying. Okay, and then again, row by column here. So this is going to be I cosine of theta. Looks like plus, well, sine of theta. Okay, and then down here, this looks like minus sine of theta plus I cosine of theta. And then here, this looks like minus I sine of theta plus cosine of theta. Okay, so I think that seems fine so far. Let's, of course, double check, and everything looks good. So here we're going to be very, very careful. Lots of room for this. Because again, when we do row by column, we have to be very, very careful. So it's going to be this product plus this product for the upper entry. So 1 times this plus negative I times this. Okay, so 1 times this plus I times this. So again, row by column. So product plus product. So this here looks like plus I sine of theta. And then if we're careful, so I times I is negative 1 times the negative, this will be plus cosine of theta. Okay, so we're going to continue in that way, just being careful. Okay, so and again, row by column here. So this will be 1 times this plus I times this. Okay, so here we go. So 1 times this will be I cosine of theta plus sine of theta. And then plus, well, I times this. So I times I is negative. So negative, negative, negative. So I think that's going to be a minus sine of theta. And then we've got, yep, so that seems good. And then we've got minus I cosine of theta. So that seems pretty good so far. I'm happy with that. Hopefully you are too. Okay, so we've run out of columns, so now we're on to the second row. So again, row by column. So this will be I times this plus 1 times this. So I times this will be, looks like minus I cosine of theta. And then here, we've got to be careful here, right? Because I times I is negative 1, but that's already negative, so that's going to be plus sine of theta. So that seems nice. Okay, so that was this times this plus this times this. Well, 1 times this should be minus sine of theta plus I cosine of theta. Okay, so now we move on to row by column here. So I want negative I times this plus 1 times this. So I times I is negative 1, but that gets negated, so that looks like a cosine of theta. And looks like minus I sine of theta. So that seems pretty good so far. And then 1 times this, so that's minus another I sine of theta plus cosine of theta. Okay, so let's tidy this up. Okay, so cosine plus cosine is 2 cosine. This plus this means I've got 2 copies of this, so let's call this 2 times cosine of theta plus I sine of theta. So that seems pretty nice. I'm happy with that. Now this looks like 0. These cancel and these cancel, so I'm really happy about that. And then here, let's take a look here. So it looks like these cancel and these cancel, so I've got another 0 here. And then cosine plus cosine, that gives me 2 cosine. So that looks like 2 times, and then adding these as well. So I've got cosine of theta minus I, because I factor the 2 out, sine of theta. And I think we're going to be sort of clever in the way we were earlier, thinking about properties of odd-even functions and Euler's formula. Let's distribute the 2 now, so we can scale each entry by, I should say 1/2. So let's scale each entry by 1/2. That gives me the following, so that'll kill that too. So I've got cosine of theta plus I sine of theta. That seems nice. A half of 0 is 0. Half of 0 is 0. And then here we could be kind of clever. So a half of 2 is 1. But I'm going to use properties of even and odd functions. So cosine of theta is the same thing as cosine of minus theta. And then this, since sine is an odd function, this could be brought back inside there. Is that nice? And so by Euler's formula, we have the following. We've got this nice diagonal matrix.